No problem.
Okay, my topic will be fast tracking in phase 2 for the ATLAS detector. Starting from phase 2. This is the, sorry, this is the wrong mode. This should be the right, yeah. Starting from run 2, back then we experienced pileup values of up to 70, as you can see here on the right-hand side. For phase 2, we expect pileup values between 140 and 200. In order to monitor the reconstruction time required, you can see on the bottom plot a high pileup run that was performed by ATLAS using the run 2 detector and the corresponding software. The reconstruction time here shows an exponential growth, so that we can state that the high luminosity LHC will become a challenge in terms of tracking. But one has also to mention that this was performed using the run 2 detector, which was not built for this scenario, as it was designed for pileup values up to 23. Also, the applied tracking settings were used completely unchanged and do not fit for this high pileup scenario. Overall, this motivates a lot the R&D for tracking algorithms. If we take a look at the timescale, then we see that the high pileup run was performed in 2017. From now on, despite COVID-19, we will have 6 to 7 years in order to prepare for this scenario. And what we can do are actually 4 different things which will form our strategy, and despite also my talk. So we can replace our detector, we can adapt the tracking, we can speed up the tracking, and we can perform R&D to include new approaches to the field of tracking. Starting from the replacement of the detector used for run 2 experienced in the meantime a lot of radiation damage and is close to the end of its lifetime. Also, the run 2 detector is not designed for that high pileup values and runs already at its bandwidth limit. As an example, the transition radiation tracker, the TRT, had about 50% occupancy with a pileup of 70. So in order to handle the future scenario, it will be replaced by the inner tracker ITK. The ITK is designed to handle pileup values of up to 200, so the upper limit of the high luminosity LHC. It consists, as you can see here in the top plot, of 5 pixel layers, which cover a pseudo rapidity interval of up to 4. Additionally, there will be 4 layer of strip detector here in blue, which cover an area of up to 2.7. In comparison, the inner detector used for run 2 covers an interval of up to 2.5. The full ITK will consist of silicon tracker, so meaning that there will be no TRT anymore. Therewith, the ITK design provides, as you can see here at the bottom plot, a approximately constant level of minimum hits in all the eta ranges. Therefore, we expect a high tracking performance for all the pseudo rapidity values, while we can minimize the pixel surface, as you can see here in this forward region design, and we can reduce the bandwidth. Overall, this piece of hardware is optimized for graphics and CPU performance for phase 2 pileup scenarios. As you can take a look at the talk of Zacharias earlier today. Taking a look at the applied tracking, since we will have a very high number of hits in all the eta ranges, we can tighten the cuts that we apply, which is most dominantly shown here in the top row for the required number of hits in our pixel in strip detector. But moreover, we can adapt the required momentum and spatial parameters as well, so that we can achieve here in the on the top plot a roughly constant level for our efficiency over the whole eta range of up to 4. While as we can tighten the cuts and require more hits, we can reduce the fake rate, here shown at the bottom plot, below the level of run 2. So overall, this performed simulations show a outstanding performance that the ITK will provide us. If we take a look at the CPU performance, then the ITK tracking is still running on the run 2 software. Thereby, the biggest contributions are, as you can see here at the central table, the silicon track finding as well as the ambiguity resolution for the ITK with a pileup of 200, as well as for the inner detector with a pileup of 20. In the case of the inner detector, there's also a major contribution shown here by the TRT and the backtracking. Overall, as a side mark, a tracking code is usually optimized for physics performance, but nevertheless, we can see that the ITK in the simulation will exceed the CPU requirements with a pileup of 200 compared to what the inner detector required for a pileup of 60. If we move this to a more global scope and take a look at the ATLAS CPU resource requirements, then there was initially an extrapolation performed from run 2, which is shown here as the gray blocks, and it showed a very fast growth over the next few years. Applying the ITK and the current reconstruction software, we can see that we already achieve a significant reduction in our requirements, while we will still require approximately 45% of the CPU in this scenario. And furthermore, this is still above the flat budget model, which is shown here as the black line. So we can, the future efforts that we have to perform until the start of the high luminosity LHC are in order to close the gap. Either, or on the one hand, we need to optimize what is already there. So our current reconstruction software, and try to optimize it in terms of CPU consumption. And the other thing is perform R&D in order to reduce CPU by inventing something new. I will first of all talk about the optimization of the current tracking software. And in order to do so, we need to take a look at the run 2 workflow actually. So we start here by clustering and space point formation. Then we will perform the seeding, here shown by the green box, perform the track finding and using the combinatoric Kalman filter. And afterwards, we will have ambiguity resolution, which does, despite pure ambiguity resolution by due to historical reasons, also whole search and neural network cluster splitting in jets. Then there are, back from the run 2 reconstruction software, also parts related to TRT and to vertexing, but this I won't discuss any further in this talk. Covered by the term fast-track reconstruction, which was originally motivated by testing whether it's possible to have a software-oriented trigger tracking for a high-level trigger, we investigated the modification of this chain. So our starting point thereby is the classical workflow you see on the right, which is from the run 2 workflow. We used the ITK geometry and we tested for pileup values of 140 and 200, as these are the edge values expected for high luminosity LHC. Our target thereby is to reduce the CPU consumption as far as possible, while we want to have a minimal loss in physics performance. The workflow can be grouped by the three topics: preprocessing, combinatorial track finder, and ambiguity resolution. And without modifications, you can see at this bottom table the required CPU by these four cases. First of all, I want to point out here the requirements of the ambiguity resolution, as this is the highest contributor to the table. So this will be our first modification, meaning we want to completely disable the ambiguity resolution. Thereby, we will lose our precise track fit. So we are aware of the fact that we will lose some tracking resolution, as well as we will lose B-tagging performance. What we then did is we offloaded some of the work from the ambiguity resolution to the combinatorial track finder, meaning we want to suppress the creation of duplicates in the first place by the combinatorial track finder, and also the combinatorial track finder should also already apply the final cuts. The cuts that we applied here in the combinatorial track finder are shown here at the table, where you can see, while in the brackets you can see the default values for the track finder. And as you can see, we tightened most of the cuts in order to achieve our goal. And by doing so, this will also speed up our track finding itself. Despite of that, we used an approximated material model, as well as approximations for the cluster corrections, but we make full use of the cluster calibration, such that the combinatorial track filter will have to estimate our final track parameters already at that stage. If we take a look at the seeding, then in run 2, the seeding required approximately 20% of CPU time. For ITK, in phase 2, we expect the value to rise up to 50%. Now, if we take a look at the number of seeds versus eta shown here in the plot, then and considering that the ITK will consist of 5 layers of pixel detector, then it's obvious that most of the seeds are produced by the pixel detector. Furthermore, the pixel detector covers the full range of eta up to 4. So our goal was to improve the seed purity and drop the strip seeding at all. Despite in improving the seed purity, we will also achieve that since we have more pure seeds, reduce time in the whole road building and track finding work chain afterwards. And as a side remark, we for the study we turned off the BREM recovery. Some further modifications that we performed was actually to speed up the pixel pre-processing, as well as the strip clustering. The strip spacepoint formation thereby is some kind of a special case, as it is expensive in terms of CPU to calculate them, while they are only required for the seeding. So what we did is we totally dropped it from the work chain. And as a side remark, in the ITK, there will be the front-end chip, which goes by the name RD53B, which will read out the pixels in a tree-like way, so that we have pre-clustered data already, which allows a significant data compression, as shown here in comparison between pixel and strips. And you can see these are approximately about the same size. But unfortunately, until now, there is no decoding software available yet. So what we did is we used the run 2 raw data decoding, and we scaled it up to the event size expected for the ITK. For Monte Carlo, we used the decoding for the root files. In these modifications I just presented, we can take a look at the performance we will achieve. First of all, the efficiencies. In the top row, you see the efficiencies for single muons versus eta. On the left-hand side for PT of 2 GeV, right-hand side for 100 GeV. As we see, we have a slightly reduced efficiency, but this is exactly what we expected from our modifications. More remarkable thereby are the reduced efficiencies in this barrel end cap transition region of the ITK, as well as in the very forward region. At the bottom right plot, we see the efficiency versus PT for a TT bar event or with a 200 pileup. And as you can see here, we lose more efficiency in the very low PT region, which is due to our approximated material model. If we take a look at the number of tracks that we receive in the top left, can you still hear me?
Yes, we do.
Okay, I just received the warning.
Unstable, but it's okay.
Okay. If we take a look at the number of tracks that we receive, then we see we have slightly fewer tracks, which is a direct consequence of our lower efficiency. While we also see that our fake rate does not change significantly compared to the default track reconstruction. If we take a look on the right to the number of hits that we have on our strip detector and our pixel detector, and we see there we are all almost identical to the default track reconstruction. If we take a look at the vertex parameters, here shown for muons, which provide the best insight. On the left-hand side for 2 GeV again, on the right-hand side for 100 GeV. We see most of the plots look very fine. Some side marks at that point are for the 2 GeV case. We see about 20% loss in our resolution, which is again a direct consequence of our material model, as in this region the multiple scattering becomes a dominant effect. For the 100 GeV case, there we see here in the Z0 region around eta of 2, we see approximately 50% loss, which is due to our cluster correction. The main message that we can learn from this is that we see the deviations, but we also understand the sources of them fully. Moving over back to the CPU requirements, then you can see here in the table a comparison between the required CPU resources, ones for the default and for the fast track reconstruction, with the main changes here again in the silicon track finding and the ambiguity resolution, as well as in the end for the total requirements in the ITK, where we achieved a factor of 6 to 7 speed up for both the 140 pileup and the 200 pileup case compared to the default track reconstruction. While this modification is valid for PT values of above 1 GeV, and it includes the full detector. Thereby, we still reused the Run2 software and did not include any benefits that we will get from ACTS in the future. Moving over to the Atlas CPU requirements, then we can learn from this study that they're able to reduce the Atlas CPU requirements drastically for phase 2. This will affect Monte Carlo reconstruction components as well as data processing, and also the heavy iron sector will benefit from them. so that we can build the message that the CPU requirements for event generators as well as for GN4 will become a dominating part, while tracking is not dominating in the CPU consumption anymore in the future. As we can naively illustrate in this pie chart for CPU requirements in the future by, let's say, squeezing the corresponding parts to what they may become. So despite the fact that the fast track reconstruction is sufficiently fast for phase 2 tracking, we also saw that the physics performance needs further improvements. And this we won't do inside the ATLAS software, but we will change the software system in order to achieve this by using ACTS. ACTS is an open source tracking project with contributors from various collaborations. And I recommend Xiaokong's talk, which I linked here, by tomorrow. It provides a modular set of tracking tools and algorithms with a simple interface to perform R&D. And this will be overall important for us to improve all types of special reconstructions like gamma B tagging and so on. Besides the development of ACTS, there's also a journey towards new harbors, looking into machine learning. There was, as an example, the TrackML challenge as a public competition event for tracking performance. There's also an ongoing effort to adapt tracking to new hardware types as FPGAs and GPUs. Also, there are inspirations and ideas like what Moritz talked about yesterday of including new ideas into the field of tracking. Overall, this shows the importance of a strong tracking community and the existing of workshops in order to improve the performance. Let me summarize what I talked about. So the high luminosity LHC will become a challenge for track reconstruction. By installing the ITK, Atlas will get the appropriate hardware to perform tracking with a pileup of up to 200. The CPU requirements thereby are very, very strict. So that's why we built the prototype for fast track reconstruction, which was purely around CPU optimization of classical tracking. Thereby, we achieved a speed of a factor of 8 with the ITK in a pileup scenario of 200 compared to the run-2 detector in a pileup of 60. So that we can conclude that the tracking won't be a dominating CPU consumer in phase 2 computing. Targeting the achieved physics performance, then we see that for a high-level trigger, this exceeds the trigger requirements. In order to apply it for offline reconstructions, there are further improvements required. This is the point where ACTS will become essential for phase 2, as it provides the ideal R&D platform for track reconstruction algorithms, and it will become beneficial to all types of reconstructions. As a last comment, besides of the development of ACTS, Atlas is also actively investing in the R&D for new concept to include them to the field of tracking with regard of phase 2. Thanks.
Thanks a lot, Fabian. Any questions to Fabian? Okay, I have one. You mentioned at the beginning that the cluster splitting, RANet cluster splitting is disabled because there is no more ambiguity. So there is no replacement right now in fast tracking for cluster splitting.
This is exactly the point where you see that the physics performance will be reduced. So yes, the whole study of fast track reconstruction was about how fast can we get with tracking. And the loss of this disabling of the neural network cluster splitting is exactly one of the effects that we will have on physics performance.
Okay, thank you. Any other questions? Okay, thanks a lot, Fabian. We can move